we present a software application for detecting human actions and falls from videos. We will show a software system capable of automatically detecting different classes of human movement. When combined with real-time video cameras, this system can be used to segment different types of movement, and be used as detectors for anomalous events such as falls. Automatic recognition of anomalous human activities and falls in an indoor setting from video sequences could be an enabling technology for low-cost, home-based healthcare systems. Detection systems based upon intelligent computer vision software can greatly reduce the costs and inconveniences associated with sensor-based systems. TILO systems applications are motivated by several factors. The increase in the aging population shall reach unprecedented levels. The percentage of persons 60 or more shall increase. At the same time, the percentage of people 15 or less is decreasing. These combined factors contribute to growing sociological and economic problems. New technology solutions shall be required to address these issues, in order to continue offering a quality of life healthcare response. One problem with unassisted elderly living alone is the health risk associated with falls, and subsequent problems associated with a fall. For example, nearly 1/3 of people over 65 years of age fall each year, and of those 10 to 15% result in serious injury. More important, 75% of those with fractures do not regain their previous level of activity, constituting a serious quality of life altering hazard. This graph shows that the elderly population in the world is expected to increase until mid-2025. Detecting human actions is in general a difficult problem that requires both image analysis and machine learning techniques. For this problem, we use a dimensionality reduction technique that maps an image sequence to a set of points in a multi-dimensional space. In this way, different classes of motion cluster in different groups. The software system is depicted in this diagram. In the learning phase, a large collection of labeled image sequences are converted into spatio-temporal templates, which capture the parts of the image in movement. These images are transformed to a lower dimensional space through principal component-based analysis. Different classes of movement become clustered in different zones of this space, thus allowing for the definition of decision boundaries. In the testing phase, a single image sequence is converted to a set of spatio-temporal templates in the same way as the learning phase. These images are projected onto the space determined from training. Next, a distance metric is used to determine the closest trained group in the multi-dimensional space. Our experiments consisted of 6 different human motions for training, which were normal walking, exaggerated walking, jogging, bending over, lying down, and falling. For each of these actions, 12 different human subjects were recorded 4 to 5 times. This photo shows representative action in our training and testing dataset. A novel contribution of this work is the development of the motion vector flow instance template. This template encodes high-velocity motions in the image sequence by observing the optical flow vectors at any particular instance. The vectors are encoded by both the direction and magnitude. Moreover, the vectors are ordered such that the highest velocity vectors are represented on the topmost layer, as shown in the right diagram. These images show an example of the construction of the motion vector flow instance template. The dense optical flow vector is obtained from the image sequence by obtaining the principal movements from a structured grid of points. The magnitude and direction of the dense optical flow is encoded in boxes, centered on the structured grid of points. The magnitude is encoded both in the size of the box and the value of the pixels, giving rise to the final image. We compared the motion vector flow instance template to both silhouettes and the motion history templates. This image shows the 3 templates obtained from exaggerated walking. As described previously, each of the motion template sequences are transformed into a set of points, forming a trajectory, through principal component transformation. In this new space, trajectories of different motions form different clusters. In order to demonstrate our software, we show an example of binary classification between normal walking and exaggerated walking. The training consists of all videos of people carrying out these two actions. This video shows the two clusters that are formed from the transformation with principal component, and then linear discriminant analysis. For clarity, only one video sequence of each action is plotted. The red points represent normal walking, while the green points represent exaggerated walking. An unlabeled test sequence was chosen from walking normal, which was not included in the training procedure. The result of projecting the test image sequence in the training space is shown in blue. As can be seen, this is mapped into the same cluster as the normal walking group. For more information related to this work, please visit us at www.mellagroup.net.